Okay, so having looked at basis forms, having looked at linear forms, it's now time to consider form fields on our path to calculus. So let's look at an example. Let's consider the following two-form field in 4D in coordinates x1 through x4. This two-form field, beta, is given as quantity x3 squared plus x4 squared times dx1 wedge dx2 plus quantity x1 squared plus x2 squared times dx3 wedge dx4. Now, what does this guy look like? Well, it's kind of hard to see, but take a look. dx1 wedge dx2 is oriented projected area in the x1, x2 plane. Likewise with dx3 wedge dx4. Now, that's kind of helpful, but what about those coefficient functions out in front? Well, those correspond to the square distance between the point at which you're evaluating things and the origin in respective x3, x4, and x1, x2 planes. So if at a point I feed beta a pair of vectors in 4D, call those u and v, then what it does is projects those vectors to the x1, x2, and x3, x4 planes. Then it computes oriented projected area in each of those planes, and then scales that area up by the squared distance to the origin, swapping the two planes that you're working with. Now, this is kind of hard to visualize. You can, in this particular case, draw a picture or two, but in general, you're going to have to rely on your algebraic understanding of these form fields. Okay, so that's one example. Let's look at another example. Let's consider the question of flux forms. What is the analog of a flux form for a vector field f on Rn? Now, I remember that in 2D, flux was a one-form field, and in 3D, flux is a two-form field. I kind of see a pattern. In both of those cases, they were measuring something orthogonal to the vector field. And in 2D, it's oriented projected length, and in 3D, it's oriented projected area. So what's it going to be in n dimensions? Well, I think you will agree with me that flux in ND should really be an n-1 form. Let's call that guy phi sub f, and what it does is it takes in n-1 vectors in Rn. Let's call those v1, v2, all the way up through vn-1. If I evaluate the flux form on those vectors, then what do I got to do? It's got to be some sort of alternating multilinear thing. Oh, that's right. It's got to be a determinant. A determinant of what? Well, we have to use the vector field f, and we have to use these n-1 vectors, and boom, that gives us an n by n matrix. Compute the determinant of that, and that's it. That's it. It's got the right units. Now, you might want to know what that looks like in terms of basis forms. And what this is going to evaluate to, as you can check, is the sum, as I goes from 1 to n, of -1 to the I-1 times fi, the ith component of the vector field, times the basis form dx1 wedge dx2, all the way up through dxn skipping the ith term. So it's as if the ith term in the volume form gets replaced by the vector field component. Now notice this makes sense. This matches what we learned in 2D, in 3D, but this works in arbitrary dimensions. Okay, so let's summarize what we have done so far. We have generalized differential forms from 3D to arbitrary dimensions, starting with an abstract definition of linear k-forms as an alternating multilinear function on k vectors giving you a scalar, just like a determinant. And these are decomposed into basis k-forms, things that really are determinants giving you oriented, projected k-dimensional volume. We can take forms and multiply them together using the wedge product, something that takes a p form and a q form, multiplies them together into a p plus q form. And finally, with all this as background, we are able to talk about k-form fields as choices of k-forms at every point in space. And that is going to lead us to calculus.